Professor Georgy Logvinovich stands before a room of Soviet Navy admirals in 1961, proposing a torpedo that will travel at 200 knots, 4 times faster than any weapon afloat. The concept sounds like science fiction. Wrap the weapon in a self-generated gas bubble, eliminating water contact and hydrodynamic drag entirely. The problem is immediate. No engineer has ever sustained supercavitation beyond a laboratory flash tank, where a test slug punctures a thin water film for a fraction of a second. The admirals lean forward, skeptical. At 200 knots, a torpedo could cross 7 kilometers in under 2 minutes, reaching a carrier group before evasive maneuvers even begin. But if the bubble collapses mid-run, water drag will shatter the hull instantly, wasting 15 years of secret funding. Logvinovich's mathematics are elegant. Water molecules cannot accelerate fast enough to close around a high-speed object if gas continuously vents from the nose. So the torpedo rides inside a stable cavity with near-zero skin friction. The theory rests on decades of hydrodynamics research, but it remains purely theoretical. Soviet Navy officials respond that no test data exists beyond laboratory flash tanks, where cavities last milliseconds. Sustained supercavitation at full weapon scale, across kilometers, not centimeters, has never been demonstrated. The gap between chalkboard equations in a deployable weapon is vast, and the admirals know it. Conventional torpedoes of the early 1960s reach a maximum speed of about 50 knots, limited by propeller cavitation and hydrodynamic drag on the hull. Beyond that threshold, water vapor bubbles form on the propeller blades, collapsing violently and eroding the metal. Drag increases exponentially with speed, so doubling velocity requires 8 times the propulsion power. Even the fastest Soviet electric torpedoes cannot break the 50-knot barrier without burning through their batteries in seconds. Logvinovich's proposal promises to leap past that ceiling entirely, but only if the bubble can be generated and sustained continuously, a feat no propulsion system has achieved. The admirals approve a research program but attach a strict condition. Without a working prototype, funding will be cut within 5 years. The Soviet Navy cannot afford to invest in theoretical hydrodynamics indefinitely, especially when submarine construction and nuclear propulsion programs compete for the same budget. Logvinovich and his team receive laboratory space, a small staff, and access to the Navy's test facilities. But the countdown begins immediately. If scaled experiments fail to produce a stable cavity, or if no propulsion system can sustain the bubble, the program ends and 15 years of research funding evaporates. Propeller-driven torpedoes cannot generate gas fast enough to envelop the entire hull. Early experiments at the Navy's Hydrodynamics lab confirm that a spinning propeller creates localized cavitation bubbles on the blade tips, but those bubbles collapse within milliseconds and never extend forward along the body. The torpedo's nose and midsection remain in full contact with water, generating the same drag that limits conventional weapons to 50 knots. Engineers calculate that sustaining a bubble for a 7-kilometer run would require venting hundreds of liters of gas per second, far beyond what any propeller wake can produce. The propulsion team concludes that a fundamentally different gas source is required. The program moves to Lake Issyk-Kul in Kyrgyzstan. The lake is 668 meters deep, isolated from foreign reconnaissance satellites by mountain ranges, and large enough for multi-kilometer test runs. But it is landlocked, so recovery operations require divers and surface vessels operating in a confined envelope. Any guidance malfunction at 200 knots would send the prototype into the lakebed or shoreline, destroying the weapon and potentially killing recovery crews. The test range offers secrecy, but no margin for error. Engineers map a narrow corridor along the deepest section of the lake, calculating that even a 2-degree trajectory deviation would put the weapon outside the safe zone within 30 seconds. Early prototype designs attempt to inject compressed air through hull ports, venting gas continuously as the torpedo accelerates. Initial tests in the lake show that the bubble forms cleanly at low speed and drag drops as predicted. But the onboard air tanks exhaust within seconds, and the bubble collapses as soon as gas flow stops. The torpedo slows to conventional speeds, and hydrodynamic drag reasserts itself. Engineers calculate that carrying enough compressed air for a 7-kilometer run would require tanks larger than the entire weapon, making the design impractical. The program needs a propulsion system that generates gas as a byproduct, not as a consumable payload. Engineers calculate that sustaining a bubble for a 7-kilometer run requires continuous, high-volume gas generation. Only a solid-fuel rocket motor produces enough. But venting exhaust aft, the conventional configuration, would superheat the rear structure and provide no bubble coverage at the nose, where water pressure is highest. The rocket gases would flow backward, away from the stagnation point, leaving the nose in full contact with water. Drag would remain nearly unchanged, and the weapon would gain speed without gaining the bubble. The propulsion team faces an impossible geometry problem. The motor must generate enough gas to wrap the entire hull, but the gas must reach the nose without melting the structure or collapsing under back pressure. The propulsion team proposes the inverse configuration. Mount the rocket motor amidships and duct exhaust forward through a perforated nose cone, generating the bubble at the stagnation point where water pressure is highest. The concept inverts conventional rocket design, sending superhot gases toward the nose instead of aft for thrust. Internal ducts would channel exhaust through the forward bulkhead, venting through a ring of holes machined into the nose cone. If the geometry works, the gas will nucleate a cavity at the stagnation point and flow aft along the hull, enveloping the entire weapon. The team sketches the concept in a single afternoon, but building a nose that survives the thermal load becomes the new critical path. Wind tunnel water tests confirm that forward venting creates a stable bubble envelope that flows along the hull. A scaled model fitted with a gas injector at the nose is mounted in the test section, and water flow accelerates to simulate high-speed conditions. Gas vents through the perforated nose, and within milliseconds, a hemispherical cavity forms at the stagnation point. The bubble grows aft, wrapping the model's midsection and tail. Drag drops by 90% compared to the same model without gas injection. High-speed cameras capture the bubble's stability. It holds its shape across the entire length of the test section, neither collapsing nor separating. The propulsion team has proven the concept at scale. Now, they must build a nose that survives the real thermal environment. The nose cone must now endure exhaust temperatures exceeding 2,000 degrees Celsius, with no room for active cooling systems. Ablative ceramics are selected, materials designed to erode in a controlled manner, carrying heat away as they vaporize, rather than conducting it into the structure. The engineering trade-off is tight. If the ceramic ablates too quickly, the nose deforms and the bubble collapses, allowing water to contact the hull. Hydrodynamic drag would return instantly, shattering the lightweight airframe at 200 knots. If the ceramic is too thick, the added weight reduces speed and range. The materials team machines a series of prototype nose cones with varying ceramic thicknesses and tests them in static rocket firings, measuring erosion rates and thermal penetration. The first full-scale prototype is loaded onto a launch sled at Lake Issyk-Kul in 1972. 15 years have passed since Logvinovich's original proposal, and this is the moment that determines whether the program survives or ends as a research footnote. The weapon is 7 meters long, 533 millimeters in diameter, and weighs just under 2 tons, matching standard Soviet torpedo tube dimensions. The rocket motor is loaded with solid fuel, and the ablative nose cone is fitted and inspected for fractures. If the nose fails during the burn, the bubble will collapse within milliseconds. Water drag will decelerate the weapon violently, and the lightweight airframe will crumple. Recovery divers will find only debris on the lake bed, and 15 years of secret funding will have produced nothing deployable. The rocket ignites. Solid fuel burns at 2,000 degrees Celsius, releasing a torrent of high-pressure exhaust gases that duct forward through internal channels toward the nose cone. The gases exit through a ring of perforations machined into the nose, venting at supersonic speed directly into the water ahead of the weapon. The ablative ceramic begins to glow orange as the exhaust temperature peaks, but the material holds its shape. Gas flow reaches several hundred liters per second, far exceeding what any compressed air system could deliver. The nose vents continuously, and the stagnation point, where water pressure is highest and would normally create maximum drag, becomes the birthplace of the bubble. Exhaust hits the water at the stagnation point, instantly vaporizing a hemispherical cavity. Water pressure tries to collapse the bubble, pushing inward from all sides, but continuous gas flow from the nose holds it open. The cavity grows in milliseconds, fed by the relentless stream of rocket exhaust. The interface between gas and water forms a thin, turbulent boundary layer where the two phases meet. High-speed photography from earlier water tunnel tests showed that this boundary remains stable as long as gas pressure inside the bubble exceeds the surrounding water pressure. The rocket motor delivers more than enough gas to maintain that pressure gradient, so the bubble does not collapse. It expands aft along the hull. The bubble grows aft, enveloping the torpedo's midsection and tail. Skin friction drops to near zero because the hull no longer touches water. Only a thin gas-water interface flows along the cavity boundary. The torpedo effectively flies through a self-generated air tunnel underwater. Only the nose cone remains in direct contact with the interface, a thin film of gas and vapor where the exhaust first meets the water. Hydrodynamic drag, which would normally increase with the square of velocity, has been almost eliminated. The rocket motor now accelerates the weapon against negligible resistance, and speed climbs rapidly. This is the sustained supercavitation that Soviet Navy officials dismissed as science fiction in 1961, proven real in a landlocked lake in 1972. With hydrodynamic drag removed, the rocket accelerates the torpedo to 200 knots in under 3 seconds. The weapon crosses 7 kilometers in less than 2 minutes, a speed no ship's evasive maneuver can counter. For comparison, a conventional 50-knot torpedo would require nearly 8 minutes to cover the same distance, giving a carrier group time to turn, launch countermeasures, and deploy screening ships. Shkval eliminates that decision window. The tactical implication is immediate. Any high-value target within 7 kilometers of the launch submarine is vulnerable, regardless of speed or maneuverability. But the rocket motor's finite burn time means the weapon cannot perform doglegs or terminal homing. It flies a straight line from launch to impact. The rocket motor and collapsing bubble generate over 200 decibels of broadband noise, louder than a commercial jet at takeoff. The acoustic signature is so intense that surface vessels and screening destroyers detect the launch instantly, even at maximum sonar range. Shkval cannot hide. The noise eliminates any option for covert approach or terminal homing, because the weapon's own roar drowns out any return echo from the target. Acoustic homing requires listening for reflections. Shkval is deaf by design. The weapon must rely on inertial guidance, preset bearing and depth programmed before launch, with no mid-course correction. The speed that makes it unstoppable also makes it loud, predictable, and impossible to retarget once fired. The prototype launches from the test sled at Lake Issyk-Kul. The rocket ignites cleanly, and exhaust vents through the nose cone as designed. Within the first kilometer, the bubble forms and holds, enveloping the hull. Speed climbs past 150 knots, then 180, then 200. The weapon is flying through its own gas tunnel, and the ablative nose cone is holding its shape under the thermal load. Recovery divers on the surface vessels track the weapon's progress by hydrophone, hearing the roar even through their hull-mounted sensors. The acoustic signature is so loud that it drowns out all other sounds in the test corridor. The weapon is performing exactly as predicted: fast, loud, and locked on a preset bearing with no ability to adjust course. Guidance is inertial only. No sonar, no wire, no terminal homing. The weapon flies the bearing and depth programmed into its gyroscope before launch, with no feedback from the environment. Any deviation from the preset course will send the torpedo into the lake bed or past the target entirely, because there is no mechanism to correct mid-flight. At 200 knots, even a 1-degree error translates to hundreds of meters of lateral drift by the time the weapon reaches the end of the test corridor. The test team calculated the corridor boundaries with tight margins, but they cannot adjust course once the rocket ignites. If the gyroscope drifts or the initial alignment was off, the weapon will miss the recovery zone and impact the lake bed at full speed. At 200 knots, the torpedo covers the remaining test range in 80 seconds. Recovery divers on the surface track the acoustic signature through their hull-mounted hydrophones, hearing the roar grow louder as the weapon approaches the end of the corridor. The noise is so intense that it masks all other sounds. The divers cannot hear their own engine or communicate by underwater speaker. The test director watches the elapsed time clock, counting down the seconds until the weapon should reach the deceleration zone. If the nose cone has ablated or deformed, the bubble will collapse and the weapon will decelerate violently, crumpling the airframe. If the gyroscope drifted, the weapon will miss the recovery zone entirely. 80 seconds pass, and the acoustic signature begins to fade, indicating the rocket has burned out. The weapon reaches the end of the test corridor and coasts to a stop as the rocket burns out. Recovery divers locate the weapon by sonar and attach flotation bags, then winch it to the surface. The nose cone is scorched black and shows deep heat scoring where the ablative ceramic eroded, but there is no structural failure. The geometry held, and the bubble remains stable for the entire burn. Engineers crowd the deck of the recovery vessel as the weapon is hoisted aboard, inspecting the nose cone under bright work lights. The ceramic ablated as designed, carrying heat away without deforming the underlying structure. 15 years of theory, 5 years of scaled testing, and 3 years of full-scale development have produced a weapon that works. Tactical officers reviewing the trial conclude that the 200 decibel signature makes pre-launch detection almost certain. Any surface group with competent sonar will hear the weapon the instant it leaves the tube, and the straight-line trajectory means targets can predict the impact bearing and attempt evasive maneuvers. Shkval cannot be used for covert strikes or ambush tactics. It is too loud and too predictable. Doctrine officers classify it as a weapon of last resort, to be fired at high-value targets when stealth is already lost and the submarine is under attack. It becomes a silver bullet, carried in limited numbers alongside conventional torpedoes, reserved for defensive salvos when no other option remains. The speed that makes it unstoppable also makes it tactically narrow. Shkval enters service in 1977 aboard Soviet submarines as a last-ditch weapon against aircraft carrier groups, loaded in limited numbers alongside conventional torpedoes. Typical loadouts include 1 or 2 Shkvals per boat, reserved for high-value targets when the submarine is already under attack and stealth no longer matters. The weapon's 7-kilometer range and 2-minute flight time make it effective against carriers and cruisers within the inner screening zone, but only if the launch platform can get a firing solution before being driven off by escorts. Doctrine restricts Shkval to defensive salvos, not offensive strikes. It is a weapon of desperation, not dominance. A bet that kinetic speed can overcome detection and counterfire when no other option survives. In 1995, Russia publicly reveals Shkval's existence at an international arms expo, displaying the weapon to potential export customers and Western defense attachés. The announcement ends nearly 2 decades of operational secrecy. Western naval intelligence confirms 200-knot performance through acoustic signature analysis, and immediately begins reverse engineering efforts to understand the propulsion and guidance systems. The revelation triggers a doctrinal shift in NATO anti-submarine tactics, with new emphasis on long-range detection and rapid counterfire to engage launch platforms before Shkval can be deployed. The weapon that Soviet officials once dismissed as science fiction becomes a reference point for supercavitation research programs in the United States, China, and Germany. In April 2000, U.S. Navy Captain Edmond Pope is arrested in Moscow after FSB counterintelligence catches him meeting former Shkval engineers and attempting to acquire propulsion specifications. Pope, working as a private defense consultant, had been seeking technical data on the rocket motor and nose cone ablation system, information still classified under Russian export control law, despite the weapon's 1995 public disclosure. The FSB had monitored all foreign contact with former Shkval engineers since the mid-1990s, and any attempt to acquire detailed technical drawings triggered immediate surveillance. Pope's arrest signals that even 23-year-old Shkval technology remains classified and actively defended, with Russia treating propulsion and materials data as strategic secrets worth prosecuting under espionage statutes. Pope is convicted of espionage in December 2000 and sentenced to 20 years in a Russian labor camp. The conviction rests on evidence that he attempted to acquire classified propulsion data, even though the weapon itself had been publicly displayed 5 years earlier. Diplomatic pressure from the United States intensifies, and after 8 months in detention, Russian President Vladimir Putin grants Pope a pardon on humanitarian grounds, citing his deteriorating health. Pope is released and returns to the United States, but the case establishes a clear boundary. Russia will publicly market Shkval as an export product while prosecuting any attempt to reverse engineer the core propulsion and materials technology that makes 200-knot supercavitation possible. More than 2 decades after the 1995 revelation, no Navy has fielded a weapon that matches Shkval's sustained 200-knot performance. The United States, China, and Germany have funded supercavitation research programs, but none have solved the propulsion guidance trade-off at deployable scale. Shkval remains the fastest underwater weapon ever operationally deployed, a record set by a landlocked test program in the 1970s, using ablative ceramics and forward-vented rocket exhaust. The weapon's tactical limitations, noise, straight-line trajectory, and last resort doctrine, have not diminished its engineering legacy. It proved that a torpedo could ride inside a gas bubble at weapon scale, transforming a professor's 1961 proposal from science fiction into a kinetic reality that no Navy has yet surpassed.